prediction, make a good prediction for child behavior, you have to have that data, know it well, and make sure within one zone you have people with similar child behavior, and put people in different child behavior in different zones.
But does that apply to the definition of districts? So when you...
Whether you're looking at microanalysis zones, TZs, or bigger district is the same thing.
So you're looking for homogeneity?
Yes. So the ideal configuration, you want to have maximum homogeneity inside a zone or a district, regardless of how big or small it is, and maximum heterogeneity between the zones. So draw the boundaries draw the boundaries so that different districts or zones have maximum heterogeneity between them.
So, do you use spatial autocorrelation or measures like that to do it?
I'm sorry?
Do you use measures like spatial autocorrelation to do the homogeneity versus heterogeneity between zones?
You could, well, usually it's, you have to consider a few conflicting requirements because you want people like in a zone for transportation, be similar age group, similar income group, and if you want to model transit or pedestrian or walkability, then you have to even try to get people who are likely to walk in one zone, people who don't want to walk in another zone, and sometimes it's hard. You pretty much meet, if you have 5 criteria you're shooting for, you meet 3 criteria, but you violate some. But overall, depending what's the highest priority, I have an example here on transit. I'm going to get to. So this is the light rail. Now, for modeling transit, so there are studies that show that people who are within 1/3 of a mile from transit or light rail are likely to walk. They would often walk and use transit. Those who are 1/3 to 3/3 away, they walk some of the time. And then beyond 2/3 of a mile away from transit, it's hard to get them to walk. So for a good representation of transit, you have to have smaller zones along the corridor. In other words, these people are very likely to walk. These are not so much likely to walk. And if you break them, you have a realistic representation of transit ridership. If you lump them together, ridership is going to undershoot. So it's going to show less than actual travel. And so when people push for a project, like if people lobby for a project, they design the zone so that they overestimate the benefit of the project. People whose agenda is to kill a project, they do the exact opposite. They try to to dilute the groups that have specific same behavior, drown them in the sea of other people, and that way it underestimates the benefit of a project. So the socioeconomic input that was collected at the polygon level, microzones up to districts, is what I covered so far. The second big input for the models are network data sets. And so there are 2 basic ways to structure a network data set, as a linear referencing system or as a connected system of connected links and nodes. And what you use depends on the purpose of the data set. So if you're going to do facility maintenance, analyze accidents, that kind of activity, the best thing is to go for linear referencing system. So here, what's a linear referencing system? So it's a segment of the road. If we want to track lanes, number of lanes, material, quality of pavement, and speed, then we have all of these 4 categories. They change as you travel along the road. Now, in a linear referencing system, there will be one graphic element, and there will be 4 tables related to it. And so if something changes, like if we want to reflect change in quality, what we do is we're not going to touch at all the graphic part, the JS part stays intact. What we do is we open the respective table when we change the attribute. Now this information in the link and node system, what we do is we break the link every time any attribute changes. So we end up, so if to reflect the change of number of lanes, we introduce a node here. To reflect change in speed limit, we introduce a node here. So we end up with a bunch of segments. And so these are the primary distinctions. Now, I hope this works because I want to show you. It is Utah Department of Transportation has a pretty sleek linear referencing system. So hope it works. Okay, so here they track, what we're tracking here are crashes, culverts, and speed zones. So watch if I here. So the first thing I want to analyze would be, say, the crash. Okay, so watch, so these, the points here, green, yellow, these are locations of different accidents over a long period of time. So as you go along the road, it will tell you where accident happens. So there is a legend for the severity. So green are minor crashes and purple are severe crashes. And so there is a table associated with it. So if I click here, I'll do one more time. So it highlights, if I go on the table and look for a particular crash, it highlights it where it is. And then it gives me the information. That will be attributes that say police report, come from police report, or anything that be for a 911 crew. So the second culverts is, I don't know if I can pull it down enough to show the culverts. Okay, so you see the second row of blue points, these are locations of culverts. And if I click on a point, it has not just text or description of relevant attribute, it has pictures, and that's used for repair purposes, so you can see like if it needs repair, what the last time it was maintained, and information like that. And so how do I go out of this? I think I'm stuck at the culvert now.
While you're stuck at the culvert, I'll say something about culverts. I'm on the, I'm Professor QB from Geography. I'm on the National Climate Assessment chapter author team for transportation, and we really featured culverts heavily in this chapter that's going to come out this probably next year. A lot of the damage from not this hurricane that just happened, but last year's Hurricane Irene took place after the storm moved inland. It created a lot of rain in places like Vermont. A lot of debris, brush, wood got swept down towards the road, where it got jammed up in the culvert, or in front of it, blocked the culvert, and then water pressure then just tore the road apart, and just, you know, in many cases destroyed a lot of bridges and a lot of roads. That was the major damage from Hurricane Irene. You ready?
Okay, well, I'm going to continue, just move on. So I think you get the idea of the benefit of linear referencing systems when you want to use it to maintain the infrastructure. So the alternative way to structure networks is link and node system. So if you're going to say probably, well, if the linear reference is so great, then why do we even care to have links and nodes? And links and nodes pretty much fragment the network way too much. Now, the purpose of having a link and node structure is if we're going to use software that's going to run network graph traversal algorithms. So anytime we want to model connectivity, we have to have a nodes and link structure. And all the algorithms, like if you go on Google and you try to find a route, shortest routes, whatever, every algorithm they're searching for all possible routes between 2 points, shortest path, quickest travel time. All these algorithms operate on nodes and link level, and they all require the data set to be organized as a network, and which means that we not just have links and nodes, but we model connectivity. So we'll have turntables, and there will be explicit information about what turns are allowed or what turns are not permitted. Now, a step further in the aviation industry, then network data sets are used to show the flight itinerary. So we're not talking here physical infrastructure, but pretty much every time an airplane flies, it's a 3D kind of it's a 3D corridor, and he has to stay within that corridor. So these schedules are decided. The decision making, the foundation of decision making are network data sets, which model connectivity. Another use of network databases would be it's considered schematics, and what it means, like when we have a network data set, we have location, even altitude for every point. Like in aviation, it will be X, Y, and Z for every value. Now, we can copy that data set and rip off the spatial components. So we kind of lose the scale to it, and then we can expand, stretch to show dependencies. So this here shows how it's network JS system that shows how a delay in one flight would propagate through the system and what kind of delay it's going to cause to other flight. So scheduling is done using network data sets from which the exact location is being removed, and only time is considered to track dependencies. And so in a good algorithm, anytime the user would make a change, it's going to warn him who else is going to be affected and how the change is going to carry over throughout the system. So this is an overview of the types of analysis you could possibly do with a network data set. I don't think it's need for me to explain about routes. An analysis I want to point out here that requires network data set and JS procedures is service area. So service area question, I mean, you stop me if that's too basic for you, but like a 911 service would have that. So they have the location and they have a very precise representation of the network. And so a service area is like, how far can you go 5 minutes from the hospital? How far? 20 minutes, 30 minutes. So anytime somebody reports an accident, so they put this location on the network and they look for whose service area is that. And so the crew that can get the quickest to that place is going to be dispatched. So here I want to talk briefly about transportation data collection. So what we do is we collect data. We have traffic counts, turning movement, speed data, and these are used. Some of the data is used to estimate the travel demand model and make sure that the parameters are appropriate, and some of it is used to validate the results. So after we run the model, we determine what the traffic is, like average daily traffic is right now in the valley. We then compare with actual traffic counts, and that's how we know if the model is good, or we need to go back and retweak it, do major minor changes to make sure that it reflects the actual traffic. So here, in a nutshell, the trend is exclusive use of satellite equipment. So people use GPS, Bluetooth, cell phone, all of these devices pretty much are being captured by a satellite that determines their location. And also for speed data, it measures the change of distance for a particular time, and it determines speed. And so we have a website in our agency. We publish traffic counts, turning movement, in travel time data. And so I am gonna see if I'll be lucky to get there without any major drama. So you're probably familiar with that, but as a rule, those type of data, usually color coding is green to red, so when you have congestion, it's usually represented in red, and like if it's optimum traffic, it's gonna be green or dark green. So it's kind of, this is being, the company that created it, they are working to improve it because we gave them a lot of things to work on, and so sometimes while they're changing the code, it's not behaving however it should, so I'll try to see if it's gonna work. What it's supposed to do is like initially how it was looking yellow, green, and that's however we want it to be. So right now it seems like, well, maybe I'll give it a bit time if it's gonna load. Last time I want to try, and then it's not going to run. So what it's doing is for every segment it calculates for every segment, it calculates travel time index and planning index. So travel time index tells you how good traffic is right now. It divides the current speed by the free flow speed. And so the best value we can have is 1. When people move at free flow speed, and now the more congestion there is, the higher the number would be for the travel time index. Another measure for level of congestion would be the planning time index, and this site, if you push on particular part.